Hi, this is TheoryStation. The program is the Rational Choice Modeling Program. The series that we're on is the Basic Formal Theory Toolkit, and this is the 9th installment in the series. In this installment, I'm just going to pick up where I left off from the previous one and talk about the model of the consumer. So I gave the setup of the model and a little bit about the geometry of the problem. That is, we saw what the consumer's budget set was, and then we talked about drawing indifference curves to get an idea of what the consumer's preferences look like. So let's continue with those things, with those ideas. Remember, the consumer is maximizing utility. So they're choosing a bundle to maximize this function subject to, and we'll be assuming implicitly here, I'm going to assume monotonicity. So I can write the budget constraint as an equality, right? So subject to this constraint that the consumer spend no more than $B, and therefore without loss of generality, we'll assume $B. Now, in terms of a picture, this is good 1, this is good 2. We've already talked about what the budget set looks like. Okay. This is B over P1, B over P2, and the consumer has some indifference curves. Let me take this bundle here, and I'm going to draw the consumer's indifference curve through that bundle, and I'm going to suppose it looks something like this. Okay. That bundle is feasible. It's in the budget set. In fact, the consumer's spending all their money on it, but it's not optimal for the consumer. Okay. Why is that? Well, assuming monotonic preferences, if I draw in another indifference curve for the consumer, the second indifference curve that I've just drawn here, this corresponds to a higher level of utility. In terms of that utility hill, it's a higher altitude than this one. Okay, but notice that this bundle here, it's on that higher indifference curve, so it's preferred to the first one, has a higher utility, and it's also affordable. It's in the budget set. So this first bundle is not optimal. Here's a bundle that's got pretty high utility. I can draw an indifference curve through that, but it's not in the feasible set. So I'm just not going to worry about bundles like that. So if you think about it, indifference curves like this are irrelevant because there's no way the consumer can afford that level of utility. The highest indifference curve the consumer can attain while choosing something that's affordable is this indifference curve here. So this bundle that I've indicated, this is actually the optimal bundle. All right. So that is a picture of optimality in the consumer model. And, it's not as straightforward as just maximizing a net benefit function, for example, but it's still not that demanding. And furthermore, we can use calculus techniques to help us figure out what that optimal bundle is. Now, in the cost-benefit example, if we looked at the net benefit function at the optimal scale, the net benefit function was just peaking, and the slope of the tangent line 0. That doesn't apply here, but there is something that comes out of this picture if you look closely. This budget line is actually perfectly tangent to this indifference curve that I drew. That tangency can be expressed in terms of calculus. That is a necessary condition for an optimal bundle, sort of like the first order condition in the cost-benefit problem. Okay, so that tangency is really an important geometric insight, and next we're going to use that to actually solve an example of this model. So I'm just going to say, note the indifference curve through the optimal bundle is tangent to the budget line. All right, let's use this idea. Now, in this general setup here, we don't have an exact functional form, but if I assume that this utility function is differentiable, so that we can use calculus techniques, there's a way of expressing that tangency in terms of equations. Okay, so what this means is that, now this is, if you haven't seen constraint optimization, it might seem a little bit mysterious, but what it means is we can look at the following system of equations. I'm going to take the partial derivative with respect to x1 of the utility function. That I'm going to set that equal to lambda times p1. I'm going to take the second derivative of the utility function, set that equal to lambda times p2, and I'm going to write out the budget constraint as well. Okay, so to analyze this optimization problem, I've written down a system of equations, and you'll note something a little funny here. There's this extra variable I've thrown in. Okay, this is called the Lagrange multiplier. And for now, just think of it as just an extra variable that we're going to solve for. It does have an economic interpretation, but it's a system of 3 equations in 3 unknowns. There's the x1, x2, that's the consumption of good 1 and good 2, plus this extra multiplier. Okay, I mean, we're mostly interested in the optimal x1 and x2, but back to my train of thought. So this tangency condition means that the optimal bundle plus this Lagrange multiplier must solve this system of equations. That's a bit of a leap, perhaps. Later on, when we're talking about optimization theory and gradients and whatnot, we'll see how this follows. But so what we've done then is we have this maximization problem. Because of this geometric insight, we're able to convert it to a system of equations that we have to solve. Okay. Now these equations could be, nonlinear. They could be messy. It could be hard or impossible to solve them. But this gives us some leverage on the consumer's optimization problem. So let's go to an example and see how that leverage can be exploited. So I'm going to assume a specific functional form, well, a parameterized but specific functional form. It's called Cobb-Douglas utility. All right, and a Cobb-Douglas utility function has the following form. The utility assigned to bundle x1, x2 is x1 raised to some power alpha times x2 raised to some power beta, where alpha and beta are just fixed parameters, and we'll just assume that they're positive. Okay. This utility function has indifference curves that look like this, just like we've been drawing before. Okay. And you can actually see that because if you take a positive number and let's ask what are the x1, x2 pairs that achieve that utility. Well, we can, if we write x2 in terms of x1 to get a functional relationship, then this is our equation or our formula for the indifference curve corresponding to utility level U bar. That, if you think about it, those indifference curves will have this kind of shape. Anyway, so we'll move on from there. So this is Cobb-Douglas utility, and so we're going to maximize this utility. Sorry. Subject to all right. So I've claimed that this geometric insight that we have translates into a system of equations. And that system is, for this special case, is the following. So let me just write this out. So if a bundle is optimal, then there is lambda such that these three values solve the following system of equations. First, the partial derivative with respect to x1 is equal to lambda times p1. The partial derivative with respect to x2 is equal to lambda times p2. And we have our budget constraint. All right. Again, this is three equations and three unknowns. These are nonlinear equations. It's certainly possible to not be able to solve a system of nonlinear equations, but these are pretty nice. So the way I'm going to do this is I'm first going to take the first two equations, and I'm going to assume x1 and x2 are both positive. We don't really have to worry about anything on the on the axes here. So we're going to assume the bundles are positive in both goods. So what I'm going to do is I'm going to divide the first equality by the second, all right? So from these two equations, I know that alpha x1, alpha minus 1, x2 to the beta, divided by this left-hand side here is equal to lambda p1 divided by the right-hand side here. Okay, and then those simplify. Right, the left-hand side is just alpha x2 over beta x1. The right-hand side is p1 over p2. Okay, so let's go with that. And now it's just a matter of taking this equation and combining that with our budget constraint to solve for the optimal bundle. All right. So what do I want to do first? So let's fine. Let's solve this for x2 in terms of x1. Okay, so that's beta p1 x1 divided by alpha p2. The budget constraint, we can solve for x1 in terms of x2. Okay, and now I'm going to substitute this equation into this one. All right, so x2 is equal to beta p1 x1, right? But x1 is equal to this. So x2 is beta p1 x1 divided by alpha p2. All right. So now let's go up here and let's just solve this thing for x2. Notice that this p1 here cancels with this p1. So let's just do this. Alpha p2 x2, I'm multiplying both sides by this, is equal to beta p minus beta, sorry, that's beta b minus beta p2 x2. So I'm going to add this to both sides, and we're going to get alpha plus beta p2 x2 is equal to beta b. And then x2 is equal to beta b. Let me put the p2 here, alpha plus beta. That is our solution for the optimal amount of good 2. So then we plug this back into our budget constraint, and we better get some expression that's symmetric. And I'm not going to go through all that algebra, but we do get something symmetric with a P1 instead of a P2. We could also solve for lambda, but for now I'm really just interested in not the multiplier, but the optimal bundle. So if a bundle x1, x2 is optimal, it has to be this one. That's really the logic we've been following. And then there's a short step to ascertain that, yes, indeed, this is the optimal bundle. We've solved for it. And again, we have a parametric solution for this optimal bundle. It's This is fairly, there's a lot of structure here because we're assuming Cobb-Douglas utility. On the other hand, though, with these parameters, we can play around with things and see how the optimal choice varies with the parameters. Now, of course, we have, two components to the optimal choice. One thing to notice is that if we increase the consumer's budget, that budget appears in both of these expressions. And if we increase that, the amount of good 1 and good 2 increases. Very intuitively, that doesn't have to be the case, but with this functional form, it is. If you, on the other hand, suppose you increase the price of good 1, well then clearly this expression we have for good 1 will go down, okay? So that if the price of good 1 goes up, the demand for good 1 goes down. Also very intuitive. Also does not have to logically be the case, but for this functional form, it is. This is actually, when we fix the other parameters and just think about this as a function of P1, this is the demand function for good 1. And we've seen here that demand is decreasing, which is intuitive. Some special things about Cobb-Douglas utility, some very special things, are the demand for good 1 only depends on the price for good 1, not on the price for good 2. That's something that, for most utilities, you wouldn't have that feature. The other thing I wanted to point out, which is related, is that the amount spent on good 1 is constant in price. In fact, if you just write it out, the amount spent on good 1 is P1 times X1. Well, we have solved for X1. And the P's cancel. So the amount spent on good 1 is just alpha beta over alpha plus beta. Okay. You can play around with this even more. You can think about changing alpha and beta, right? If alpha increases, the weight on the consumption of good 1 increases, and then you can see that the amount spent on good 1 increases. I think that's enough said about Cobb-Douglas utility, but hopefully this shows how that geometric intuition translates into conditions from calculus that allow us to work with this kind of optimization problem. Again, these methods are super general and go beyond just consumers, but this is definitely one of the more important models in the toolkit.